Hey, what's up, dudes and dudettes? Brad the Guitarologist here. A while back, I did a video on I've done a couple videos actually, on a Guild amplifier. I'll put some links up here. You can go check those videos out that I've already done. In the process of making those videos, we discovered that the B plus was really low in the amplifier. So I've ordered a GZ34 to install in this thing. I've also gotten a choke to install in it because as we discussed, it was a little bit noisy. By the time I had done all of the modifications I had done, which you can see again in the last video, I'll put a link up here, it was still slightly noisy. It wasn't bad, but this was the only improvement that I would really recommend beyond what I had already done. And the customer wanted to go for it. When he saw my comments in my video, he saw the video, he said, yeah, why not? Let's just go ahead and install a choke. So in this video, we're gonna run some tests on this thing. We're gonna look at the B plus. We're gonna see how much this GZ34 raises the B plus and how much it actually goes toward raising the overall plate dissipation of the output as well. And gets it a little bit closer to a maximum that we could sort of live with. Also, while we're at it, we will go ahead and put a microphone in front of the speaker, and we'll crank the thing up and do some noise tests with it probably totally dimed out, and then also with it all the way down at idle. We'll just listen to the speaker noise, the hum, and then we'll compare afterwards and see if the choke does anything to mitigate some more noise. So it should be interesting, if nothing else, out of just sheer scientific curiosity and experimentation, to see what happens when we install these two components. So if that sounds like something you'd be interested in, stick around. Okay, we're going to do some measurements on this amp. Like I said, we're going to use a close-up microphone, a dynamic mic, and I'm also using an overhead mic, which I'm going to leave on. Here's what it sounds like without the overhead. The overhead is a condenser mic, so it picks up, a lot more that's going on in the room, any air movements. But before we get too deep into this, I want to talk a little bit about just chokes in general. There are two different styles of circuit in which you will usually find a choke, at least in a guitar amplifier. Okay, this figure 30.1F, this is a basic circuit diagram with a full wave rectifier and a condenser input filter. Okay, this is the configuration that you're going to see on 99.9% of all guitar amplifiers right here. This. So what you're going to have is a condenser or a capacitor here of some value, and then you will have a choke after that. Over here is your rectifier. Here's your power transformer. So all of your voltages are originating over here and flowing this way, or the current's flowing this way. So this is a capacitor input filter with the choke in series here between these two capacitors, capacitor 1 and capacitor 2. Down here is a different style that you will almost never see, and the reason you'll almost never see this style with a choke before the capacitor, and there's a couple different ways you could do this. You could do this with the choke in between the transformer center tap as shown here and ground, or you could take this and put it up here, just right off of the rectifier. Either one of these is pretty much the same, and you will almost never see this. And the reason you will almost never see this is because mathematically, when you calculate out the size in henries of this component that is necessary for this circuit to work, it requires a larger choke if you put it here as opposed to if you put it here. So just as a cost-saving feature for guitar amplifiers, this, like I said, 99.9, probably 0.99% of all guitar amps will follow this configuration here, and almost never this configuration here. Okay, there may be some really high-end amplifiers that use this, hi-fi stuff or something that go with this, but you'll almost never see this in the guitar world. This is what you'll see more often. This is the Bible in terms of tube gear. This is the RCA Radiotron Designer's Handbook. 1,500 pages this book is. I probably never will read every single page in this book, but I do reference it. This was given to me actually by my friend Steve. I didn't have a copy of this. I have the earlier version, like I think it's, version 1 or 2, the first or second printing. But it goes into a little bit. If you wanted to really get technical with it, you could do that. If you come over here, for instance, you can see on this graph for a given direct voltage at the input to the filter. So and by the input to the filter, we mean this point right here. So if you were to measure the voltage right here to ground and get that voltage potential, that's what you're plotting up here. So let's say that right there is 400 volts. So you come up here to this, and the load will be whatever is measured in milliamps from this point to this point on the output of this circuit. For instance, let's just say our load is 60 milliamps. So 460, if you were to follow these lines up and over, it will tell you basically about what reading in henries you want your inductor to be. So this is 1 Henry down here on this line, for instance. That's 2 Henries, 3 Henries, 5, and 10. Now the thing is, if we go to the most used, or the most common, I guess I should say, we'll check out a couple of the most common rectifiers in the other Bible, which is the RCA Receiving Tube Manual. If we go to the 5AR4, which is what we're going to put in this, it will give you a filter input choke value that's typical. So it gives you this value as 10 Henries. That's probably a bit excessive. What they're doing here is they're giving you a value that will work in practically all cases for that tube. The 5U4, same story. It gives you more graphs with the 5U4 than it does the 5AR4. It doesn't give us the full, it doesn't graph it all out for a 5AR4. So unfortunately, this is kind of an incomplete tube data sheet for the GZ34. And if you wanted to be on the safe side, you could slap a 10 Henry. Anything between a 5 and 10 is going to work, really. And what we have bought here is a 5 Henry. And you can actually look this up. It's a 5 Henry at 50 milliamps. This one was made in Canada by Hammond. We could have gotten one that had a higher DC resistance. For instance, I think this DC resistance is like 210 or 220 ohms, something like that. You could get different DC resistances, different handling in terms of milliamps, and also different Henry inductance values on these things. And some of them are kind of specialized. The very common ones are going to tend to be cheaper, unless they're out of stock. Maybe you might have to back order something. But the common values, like 5 Henry is very common, and 4 Henries is very common, because a lot of Fender amps would use 4 and 5 Henries for their chokes. And this is very close to what Fender would have used for an amp of this style. So that's why we bought that. And it's just funny to me that even Fender is undervaluing the chokes in most of their amps like that, whereas this one, calls for like a 10 Henry. If you're using a GZ34 or a 5U4, most of the Fenders that have these tubes will be like 4 or 5 Henries on the choke if it's a smaller amp. So it just really depends. And there's no hard and fast rule for it. You just need to pick something usually between 5 and 10 Henry is going to be fine. So this one is going to work for our circuit, I do believe. But the first thing I want to do here, before we do anything else, is get a loudness on the noise. So this is with the volume all the way down. And now I'm going to turn, and this is in beast mode, volume all the way down. Now we're going to turn both volumes all the way up. And now I'm going to put it in normal mode with the volume all the way up. And now with the volumes all the way down. Okay, and another note about chokes that you really want to consider when you're considering whether or not to install a choke on an amp is how important is it to you that you preserve the longevity of your rectifier tubes, because a choke is going to do just that. If you put a choke in a power supply, your rectifier tube is not going to be as taxed over the long term. Okay, this is probably a good time to pause and take a look at what chokes are and what they actually do in layman's terms. A choke is an inductor, which is essentially just a coil of wire. This coil can be wound around nothing but air, or it can have an iron core or a core made from some other ferrous material, but essentially it's just a coil of wire. This coil will usually have a pretty low DC resistance. In the case of our choke here, the measured DC resistance is about 270 ohms. But inductors by nature do something that simple resistors do not do. They create a magnetic field around them. The strength of this magnetic field increases as the current in the circuit is increased, and it also varies depending on the construction of the coil, the type and size of wire, and the type of core used. An iron core, for instance, will produce a stronger magnetic field than just air alone. But inductors also do something else which is peculiar to this type of component. They resist changes in current flow. Just like the inertia of a parked bus means it's hard to get moving when pushed, so too is it hard to get current to flow through a choke when a circuit is first turned on. But also, like a bus, once things get moving, the pushing becomes easier, until finally inertia is actually helping you keep the bus going. Then it will become hard to stop. In fact, if you remove current from an inductor without providing it some way to bleed off its voltage potential to ground afterward, it can cause an arc. This is the principle behind how stun guns work, the high voltage arc being created by a discharging inductor. An inductor can be thought of as the inverse of a capacitor. While an inductor resists a change in current, a capacitor resists a change in voltage. And while a capacitor stores excess voltage as a charge, an inductor stores excess current as a magnetic field. In both instances, energy is conserved in one form or another. And while capacitors help smooth ripple in a direct current circuit through their charge-discharge cycles, an inductor does the same thing by creating something called a back EMF, or backwards electromotive force. This simply means that whenever a ripple in the direct current occurs, and the change is resisted by the inductor, its stored energy in the form of the electromagnetic field expands and collapses at the same frequency as the ripple. When the current spikes up, the extra energy gets stored up in its electromagnetic field, and thus that field expands with a slight lag. However, when the ripple is on the downward part of the cycle and the current is going down, there is a sort of vacuum that occurs which not only borrows the energy stored up in the electromagnetic field to make up the difference, but there is actually a reverse voltage which occurs where the output of the choke is now more positive in charge than the input. All of this back and forth happens in the blink of an eye, 120 times per second to be precise in the case of a full-wave rectified DC circuit in North American line frequency. So what this means in practical terms is everything downstream of a choke, all of the capacitors and resistors and tubes and other components, they'll see fewer sudden changes in current, which will not only help mitigate hum in a circuit, but will also prolong the life of all of these components. I think this will be about the third or fourth time I've pulled this chassis. Because every time I put it all back together and put it in there, I end up going back to the customer and talking about more things that could be done, to improve the amp. And, to his credit, he's somebody obviously who wants to make it the best he can make it, so that's really nice, and it's refreshing, because sometimes you get somebody who doesn't want to do very much to it or wants to keep it completely original, and that's fine, and that has its place. But with something like this, it's really cool that I was kind of given carte blanche on a few things to experiment. Just makes it a lot more fun. Definitely a more fun video if you can do that. Okay, this choke is going to have to be installed somewhere on the back side of this thing, so we're going to have to pull this out completely. All right, I think the spacing on this is about 2 inches on the holes, and it has to go on the back side. Like I said, I'm hoping it will go right there somewhere. So I'm really hoping without drilling. And oh man, it's so close. It is so close to going right there. Okay, I finally got one screw in on this side. But this one won't fit, so I'm gonna have to drill another hole right here, which is fine. It's not gonna be that big of a deal, but we'll go ahead and get that done. That is installed. Good deal. All right, I'm gonna clean up this mess on the desk, and then we will, I think probably, we'll go ahead and put it back in the cabinet, I think, and get the rest of our measurements. Okay, so here we go with test number 2. This is with the choke installed. This is with the same rectifier tube. Let's go ahead and fire her up. I'm gonna dial it up slowly, actually, just to make sure I didn't miswire anything. I mean, there's nothing to miswire. Okay, so here we are with the amp all the way back up. It's dialed up to full voltage. The volumes are all the way down on beast mode. So compare that to before. And now I'm going to turn, and this is in beast mode, volume all the way down. Now we're going to turn both volumes all the way up. Anyway, so that's it. There's our test for that. Let's go ahead and get some measurements. I want to keep this rectifier in it. I want to measure the plate dissipation on these output tubes. And I'll show you what I mean when I say that this thing is, I think it's just really under-spec'd on the power transformer. I'm just going to hook up one bias probe on this output for now. I'm not going to do 2 different probes. We don't need it. I'm just wanting to measure the plate dissipation per side, so this will give us a good idea. They're both going to be pretty similar anyway. This is a homemade bias probe that I made myself. There is a video showing you how to make one if you want to make one yourself. It's not hard. All you need is one of these really cheap multimeters you can find at Harbor Freight, and this one we're just using this to measure the plate current. What it's doing is it's splitting the connection with the plate, the tube plate and the socket, so that we can get an actual measurement. It's running that through here to measure current, and then on this one I'm going to have to take this back off yet again because I've got to hook onto the cathode. I think the next set of probes that I make, if I make another one of these, I'm going to make a tap for the cathode so I can come right off of the cathode to get my plate voltage measurement without having to open the amp up at all. All right. So we're going to go to right there, the cathode, and this one we will hook right here. So that's going to get our plate. This one will be our plate voltage, and this one will be our plate current. So we'll be able to easily see both at a glance. Okay. So once again, I've got this meter. The ground on this meter is going to the cathode of the output, and the 2 tubes share a cathode, so I'm just coming right off of the bias resistor. For the positive lead, I'm going right here, and it doesn't matter which on this because this is just in the line, so for the plate. So let's go ahead and fire it back up. All right, take it off of standby. And you can see the plate voltage here, 302 volts, 25.1 milliamps. So let's do a calculation there on that. Yeah, it's getting some buzz from the chassis. The chassis like, see, it's like just a physical, kind of almost a rattle. I gotta see if there's some way to stop that. I mean, it was doing it before a little bit also, so I don't know. Anyway, 303 plate volts times 0.0245, and that's 7.42 watts per tube. All right. Now let's shut it off and replace that rectifier and see how our numbers change. All right, back on. Our previous plate voltage was 303 volts, so we're looking for this to be hopefully higher. And the hope is obviously that it'll be by a significant amount. It is. Look at that. So it went from 303 volts up to 351 volts. The current is also higher, so we've got a little more voltage and a little more currents out of this. Okay, so let's do the calculations now. 353 times 0.0292, and that's 10.3 watts. Our trim still works. And we don't have any problems with everything cranked. All right, so I would say that that's a success. We've gotten this thing, I believe, about as good as this amp can ever be. Yeah, I really believe that this thing is a rock and roll machine. And if he's not happy with this, then by all means he can send this back to me and I'll be happy to own it. So anyway, so that will do it for this 1959 Guild, what is this, a 66J. I hope you guys have enjoyed this series. It wasn't intended to be a series, but it sure turned into one. But yeah, man, I think it's been definitely a learning experience for everybody here, hopefully, and really turned into a nice, cool amp. So that'll do it. Hope you guys enjoyed. For now, make sure you hit subscribe down below, and we will see y'all later.